To tear a single kilogram of dead mass from the grip of Earth's gravity, you must ignite a chemical inferno capable of releasing tens of millions of joules of energy. You must violently eject matter downward at supersonic velocities, riding the sheer kinetic shockwave of a controlled explosion just to overcome the curvature of space-time dragging you back to the dirt. But this raw, brute force is not the actual problem. The true nightmare of orbital mechanics is a mathematical paradox dictated by physics itself. To carry a payload into the void, you need propellant. To carry that propellant, you need a larger fuel tank. To lift that larger tank, you need heavier engines. And to lift those heavier engines, you need exponentially more It is a vicious, inescapable feedback loop. Because of this cruel mathematical reality, over 90% of a rocket sitting on the launch pad is nothing but highly explosive liquid. The actual machine, the cold metal, the intricate avionics, the cargo, the fragile human body is merely a statistical rounding error strapped to a flying bomb. For over 6 decades, humanity's solution to this equation has been as primitive as it is wasteful. We claw our way out of our planetary gravity well by deliberately shedding pieces of ourselves along the way. We build monuments of precision engineering, towering structures of aluminum lithium alloy, copper, and titanium, only to hurl them into the ocean or let them burn into a rain of ash in the upper atmosphere. Imagine purchasing a commercial jet airliner for hundreds of millions of dollars, flying it across the Atlantic exactly once, and then intentionally crashing it into the sea upon arrival. That is the accepted, undisputed history of human spaceflight. Now, as we face the terrifyingly vast and lethal expanse between Earth and Mars, this paradigm is fracturing. We are standing at the absolute precipice of our expansion into the solar system, yet the aerospace world is torn between two fundamentally incompatible philosophies of survival. Two distinct architectures are currently locked in a quiet, high-stakes war for the future of our species. One relies on the brute force heritage of a disposable past, burning vast fortunes in a single, unrepeatable flash of glory. The other wagers the entire future of deep space exploration on the radical, highly volatile premise of total reusability. The path we choose will determine whether the red planet becomes a thriving new frontier or an unreachable graveyard in the dark. If you seek the unvarnished truth hidden within the mechanics of our universe, subscribe and join us on this journey. Because the physical reality of leaving this planet is far more unforgiving than our intuition suggests. And the battle to conquer Mars does not begin with steel or fire, but with a mathematical limitation that has imprisoned us since the dawn of the 20th century. In the winter of 1903, the parameters of our cosmic confinement were quietly published by a deaf, reclusive schoolteacher in the snowbound provincial town of Kaluga, Russia. Decades before the first artificial satellite would emit its lonely radio pulse in the dark, Konstantin Tsiolkovsky mathematically proved that humanity was effectively trapped on Earth. He did not achieve this through the observation of the heavens, but through the cold, unyielding mechanics of momentum. What he codified is now known as the ideal rocket equation, and it is less of a scientific formula than it is a death sentence for human intuition. At its core, the equation reads as follows: delta underscore V equals V underscore E asterisk ln m underscore 0 per meters underscore F. This unassuming string of symbols dictates the absolute limits of what is physically permissible in our universe. To understand the gravity of our situation, we must strip away the romance of space exploration and look directly into the machinery of this formula. The term on the left, delta V, or delta V, is the supreme currency of the cosmos. It is not a measurement of speed, but a measurement of capability, the total change in velocity a spacecraft can achieve. In space, distance is largely irrelevant. What matters is the energy required to transition from one orbital state to another. If you wish to leave the launch pad, you spend delta V. If you wish to intercept the moon, you pay the toll in delta V. And if you wish to arrest your terrifying plunge into the Martian atmosphere, your survival is dictated entirely by whether you have enough delta V remaining in your tanks. On the right side of the equation lies the executioner's block. The variable V_E represents the effective exhaust velocity of the rocket's engines. This is the maximum speed at which the violent chemical combustion of propellants like liquid oxygen and refined kerosene can be forced out of the engine bell. It is a hard physical limit governed by the laws of thermodynamics and molecular chemistry. But the true horror of Tsiolkovsky's work lies in the natural logarithm, ln, and the mass ratio, m_0 per meter_f. This ratio compares the initial mass of the fully fueled rocket to the final, dry mass of the empty vehicle. Because of the natural logarithm, if you want to linearly increase your spacecraft's capability to maneuver in the void, you must exponentially increase the amount of highly volatile fuel you bring with you. Our biological intuition completely fails to grasp the severity of this exponential punishment. We evolved in a low-speed, high-friction environment. When we wish to travel further on a highway, we simply add a slightly larger fuel tank to our vehicle. The additional weight of the fuel is negligible compared to the mass of the car and the friction of the tires against the asphalt masks the underlying physics. But a rocket is a vehicle that must carry its own reaction mass into a frictionless void, fighting the relentless inverse square acceleration of a planetary gravity well. Every single kilogram of propellant added to the tank requires its own dedicated propellant just to lift it off the ground. The math cascades into a catastrophic feedback loop. To achieve orbit, a single-stage chemical rocket would need to be roughly 96% fuel by mass. The remaining 4% must account for the engines, the guidance computers, the structural tanks, the payload, and the fragile biological cargo. The margin of error is virtually non-existent. Because of this equation, the human perception of spaceflight is built upon a fundamental misunderstanding of what it actually means to go to space. When we look up at the night sky, we imagine space as a place located far above our heads. We think of rockets as high-speed elevators, fighting gravity in a vertical ascent. But going up is trivial. The recognized boundary of space, the Kármán line, is a mere 100 kilometers above sea level. You could drive that distance on an interstate highway in less than an hour. If a rocket only needed to reach space, it could be a relatively small, simple machine. It would breach the atmosphere, experience a few fleeting minutes of weightlessness, and then immediately fall back to Earth like a stone thrown into the air. The profound, agonizing engineering challenge is not getting to space. It is staying there. Orbit is not a destination. It is a velocity. To avoid plunging back into the atmosphere, a spacecraft must pitch over and accelerate sideways with such ferocity that as Earth's gravity pulls it downward, the curvature of the planet continuously falls away beneath it at the exact same rate. You are not floating in orbit. You are in a permanent, terrifying state of freefall, missing the ground because you are moving at roughly 28,000 kilometers per hour. That is Mach 23. Achieving this absurd lateral velocity requires an oceanic expenditure of delta V, placing immense strain on the structural integrity and thermal limits of the vehicle. Historically, humanity did not solve the tyranny of Tsiolkovsky's equation. We simply circumvented it through an act of mechanical desperation known as staging. Since we could not build a single vehicle light enough and powerful enough to reach orbit intact, we built towering, segmented leviathans designed to systematically destroy themselves during ascent. Consider the sheer, unapologetic violence of the Saturn V rocket that carried Apollo astronauts to the moon. It was a skyscraper of aluminum and cryogenic liquid, weighing nearly 3 million kilograms. As it thundered upward, draining its cavernous first-stage tanks at a rate of 15 tons of propellant per second, it was rapidly accumulating dead weight. The massive F-1 engines and the vast, empty fuel tanks were no longer producing thrust. They were an anchor, dragging the vehicle back toward the dirt. To survive the mathematical trap of the mass ratio, the rocket had to shed its own mass. Through the use of pyrotechnic fasteners and explosive bolts, the vehicle literally detonated its own structural connections in the upper atmosphere. Searing plumes from ullage motors shoved the spent lower stage away, allowing the upper stage to ignite its engines in the vacuum. The first stage, a marvel of aerospace engineering worth millions of dollars, was casually discarded to plunge violently into the Atlantic Ocean. This process was repeated, stage by stage, until a minuscule fraction of the original vehicle finally reached the lunar surface. Staging is a concession to the laws of physics. It is the orbital equivalent of a starving wolf gnawing off its own frozen leg to escape a steel trap. It is a brutal, wasteful philosophy of subtraction, built on the premise that the only way forward is to leave a trail of multi-million-dollar wreckage in your wake. For a brief, naive period in the late 20th century, the aerospace industry believed it could escape this paradigm with the space shuttle. The promise was intoxicating. A sleek, winged spacecraft that would launch like a rocket, operate as a laboratory in the void, and land on a runway like a commercial airliner. It was supposed to be the dawn of true, economical reusability. But the universe is fiercely intolerant of compromise, and the shuttle became a victim of the very physics it tried to domesticate. The shuttle exposed the second, equally terrifying half of the orbital mechanics equation, re-entry. To safely return a massive, winged vehicle from a velocity of Mach 23, the vast kinetic energy of orbit must be violently converted into thermal energy. The spacecraft acts as a blunt, hypersonic plow, compressing the tenuous upper atmosphere ahead of it into a superheated plasma shockwave. The silica-based thermal protection tiles on the shuttle's belly routinely absorbed temperatures exceeding 1,650 degrees Celsius, glowing incandescent as the vehicle surfed a microscopic line between controlled deceleration and total atmospheric vaporization. But the shuttle was not truly reusable in the way a commercial jet is reusable. Its solid rocket boosters, heavily corroded by salt water upon ocean splashdown, required massive industrial overhaul. Its external fuel tank, the largest component of the entire stack, was completely disposable, burning up in the atmosphere on every single flight. And the orbiter itself required hundreds of thousands of hours of painstaking, microscopic inspection and refurbishment after surviving the trauma of re-entry. The heat shield tiles were so fragile they could be damaged by the impact of a simple pen dropped by a technician. The space shuttle was a magnificent engineering achievement, but philosophically, it was a disposable rocket masquerading under the illusion of reusability. It proved that in the unforgiving environment of low Earth orbit, half measures are paid for in billions of dollars and, tragically, in human lives. Now, as the crosshairs of human ambition shift from the barren, familiar dust of the moon to the alien, rust-colored dunes of Mars, the mathematics of survival scale up to a level that borders on the impossible. The journey to Mars requires more than just achieving the grueling Mach 23 required for low Earth orbit. It demands an entirely new, massive injection of delta V to shatter the invisible chains of Earth's gravitational sphere of influence. A spacecraft must burn its engines to execute a transmartian injection, threading the needle of a Hohmann transfer orbitan elliptical path stretching hundreds of millions of kilometers through the irradiated vacuum of interplanetary space. If we attempt to force the legacy architecture of disposable multi-stage rockets onto a crewed mission to Mars, the Tsiolkovsky equation demands a vehicle of such apocalyptic proportions that it defies economic and industrial reality. To land a meaningful payload on the Martian surface and return a crew alive using disposable hardware, the initial mass required on the launch pad back on Earth would dwarf the largest structures ever built by human hands. You would need thousands of tons of propellant simply to push the propellant that will push the payload. The cost of throwing away such a monumental assembly of aerospace hardware in a single mission would bankrupt nations. We have hit a wall. The disposable methodology that carried us through the Cold War is mathematically incapable of sustaining a permanent, multiplanetary civilization. We cannot colonize the solar system by throwing away our ships any more than maritime explorers could have colonized the New World by burning their galleons upon reaching the shore. The realization spreading through the highest echelons of propulsion laboratories and engineering firms is chilling. If the physics of chemical propulsion cannot be changed, and the natural logarithm of the rocket equation cannot be bargained with, then the entire architecture of spaceflight must be torn down to its foundations. We are left staring at an abyss, knowing that to bridge the dark, lethal gulf between Earth and Mars, to comprehend the sheer, suffocating scale of the architecture required to bridge the abyss between Earth and Mars, we must first confront the geometry of the void itself. The expanse separating our pale blue dot from the red planet is not merely an empty, static canvas. It is a hostile, irradiated ocean governed by celestial mechanics that operate with an indifferent, grinding precision. We are attempting to fire a microscopic projectile from a moving platform that is traveling at 30 kilometers per second around the Sun, to intercept another moving target millions of kilometers away, traveling at 24 kilometers per second along an entirely different orbital curvature. This celestial choreography is bound by rigid mathematical windows. Because Earth and Mars orbit the Sun at different speeds and different distances, they only align favorably for a journey once every 26 months. This is known as the synodic period. If you launch a day too early or a day too late, the agonizing mathematics of the Tsiolkovsky rocket equation exact a brutal toll. You will either require an exponentially larger volume of propellant to brute force the trajectory, or you will miss the planet entirely, drifting into an eternal, lethal orbit around the Sun. The standard trajectory, the Hohmann transfer orbit, is an invisible elliptical highway requiring roughly 4.3 kilometers per second of delta V just to break free of Earth's gravitational chokehold and coast toward the Martian intercept. But coasting in deep space is not a passive, peaceful drift. It is an act of survival in an environment actively trying to dismantle human biology. Beyond the magnetic shield of our planet, a spacecraft is bombarded by a relentless crossfire of radiation. Galactic, cosmic, atomic particles accelerated to near the speed of light by distant supernova tear through steel and human tissue alike, like microscopic shrapnel, shattering DNA strands and rewriting our cellular code with malignant errors. Solar particle events, massive storms of high-energy protons hurled by our own star, can dose an unshielded crew with lethal radiation in a matter of hours. And compounding this physical terror is the psychological isolation of the speed of light. At its maximum distance, Mars is nearly 400 million kilometers away. Radio waves, the fastest messenger in the universe, take 22 minutes to cross that dark gulf. If an engine misfires, if a hole breaches, if a fire erupts in the life support module, you cannot ask Earth for help. By the time your desperate transmission reaches mission control, and by the time their frantic response returns to you, 44 minutes will have passed in the cold silence. You are utterly, terrifyingly alone. Faced with this monumental barrier, the aerospace establishment birthed a leviathan constructed from the legacy of the Cold War. The Space Launch System, or SLS, is a machine that represents the absolute apex of the disposable architecture paradigm. Standing over 300 feet tall and weighing millions of kilograms, it is less of a vehicle and more of an industrial monument engineered for self-destruction. The core stage of this behemoth is a towering cylinder of aluminum lithium alloy, a structure machined to tolerances of microscopic fractions of an inch, designed purely to contain the most volatile, difficult propellant combination in the universe, liquid oxygen and liquid hydrogen. We must speak of liquid hydrogen, for it is the dark, temperamental soul of the traditional space program. It provides the highest efficiency, the highest specific impulse of any chemical rocket fuel, but it extracts a terrible price for its power. Hydrogen is the smallest, lightest element in the cosmos. It does not want to be contained. To keep it in a liquid state, it must be cryogenically frozen to minus 253 degrees Celsius, just 20 degrees above absolute zero. At this temperature, the cold is so profound that it alters the very molecular structure of the rocket's hull. Metals become brittle, shrinking and warping. The hydrogen atoms are so minuscule they can slip through the microscopic crystalline lattice of solid steel, pooling in invisible voids and creating a terrifying hazard known as hydrogen implosion. If a single microscopic spark encounters a hydrogen leak as it boils off into gaseous form, the entire vehicle vanishes in an invisible, supersonic shockwave. To turn this temperamental frost into thrust, the SLS relies on 4 RS-25 engines sitting at the base of the core stage. Calling an RS-25 an engine is a profound understatement. It is a masterpiece of thermodynamics, a controlled explosion contained within a labyrinth of regenerative cooling channels. The heart of the RS-25 is its turbopump, a piece of rotating machinery no larger than a standard car engine, but one that generates over 70,000 horsepower. It forces the cryogenic liquids into the combustion chamber at hundreds of gallons per second, operating under immense pressures and temperature gradients so extreme that one side of a metal bearing is subjected to absolute freezing cold, while the other side is exposed to the searing heat of a 3,000-degree plasma flame. When the countdown reaches 0, these 4 cryogenic masterpieces ignite, but they are not enough to lift the impossible weight of the fully fueled rocket. To break Earth's grip, the SLS relies on 2 massive solid rocket boosters strapped to its sides. These are essentially 2 towering pipes packed with over 1 million kilograms of ammonium perchlorate and aluminum powder. They are solid-state bombs. Once the ignition sequence flashes down the central core of the boosters, they cannot be throttled, they cannot be shut down. They burn with a ferocious, blinding violence, generating millions of pounds of thrust in an apocalyptic roar that literally melts the launch pad beneath them. And then, the ultimate tragedy of the disposable architecture unfolds. 2 minutes into the flight, the solid rocket boosters expend their fuel, become dead weight, and are explosively ejected into the ocean. 8 minutes into the flight, having dragged the payload into the upper atmosphere, the immense core stage runs dry. The RS-25 engines, thermodynamic miracles that took tens of thousands of hours and hundreds of millions of dollars to build, shut down. Explosive bolts sever the connection, and the entire core stage is discarded. It falls back into the atmosphere, the friction of re-entry tearing the delicate aluminum lithium tanks apart, the heat melting the intricately machined turbopumps into glowing slag, raining a shower of molten ash into the Pacific Ocean. The SLS successfully conquers the rocket equation by feeding pieces of itself into the furnace of physics. It is a system built on the premise that humanity is rich enough to throw away a skyscraper covered in priceless jewels every time we wish to step outside our own front door. On the opposite end of the engineering spectrum lies an architecture so violently radical, so fundamentally opposed to the heritage of aerospace engineering, that it was initially dismissed as science fiction. Starship. When you first look at the Starship system, your intuition rebels. It does not look like a modern rocket. It looks like a crude, retrofuturistic silo born from the mind of a mid-century pulp novelist. It is a monolithic cylinder constructed entirely of cold-rolled 30X series stainless steel. For decades, the aerospace industry has viewed steel as an antiquated, heavy material, abandoning it in favor of carbon fiber composites and lightweight aluminum alloys. But out in the lethal extremes of interplanetary space, steel possesses a terrifyingly beautiful duality. Under the bone-chilling cold of cryogenic propellants, steel does not become brittle and shatter. Its crystalline structure tightens, and it becomes vastly stronger. Conversely, during the blistering, ionized plasma inferno of atmospheric re-entry, steel requires significantly less thermal shielding than aluminum because its melting point is profoundly higher. It is a material chosen not for its elegance, but for its sheer, undeniable durability. It is built to endure the violence of orbit, to return, and to fly again. But the hull is merely the armor. The true, beating heart of Starship is an engine that ventures into the absolute darkest arts of propulsion mechanics, the Raptor. The Raptor does not burn hydrogen. It burns a mixture of liquid oxygen and liquid methane. Methane is denser, easier to store, and crucially, it can theoretically be synthesized on the surface of Mars through the Sabatier reaction, using the Martian carbon dioxide atmosphere and subsurface water, ice. But it is not the fuel that makes the Raptor terrifying, it is the plumbing. The Raptor operates on a full-flow, staged combustion cycle. In the history of human spaceflight, prior to this engine, no organization had ever successfully flown a full-flow engine to orbit. It was considered the holy grail of rocketry, a theoretical pinnacle of efficiency that was deemed too dangerous, too complex to master. In a traditional engine, a small amount of fuel and oxygen is burned in a separate gas generator simply to spin the turbines that pump the main fuel. And the exhaust from this little turbine is dumped overboard, wasting precious delta-V. In a full-flow system, there is no waste. Every single drop of propellant is utilized. To achieve this, the Raptor uses not one, but two preburners. One burns a heavy mixture of oxygen with a little methane, generating a violently hot, high-pressure, oxygen-rich gas to spin the oxygen turbine. Pumping hot, highly pressurized, gaseous oxygen is an engineer's worst nightmare. Oxygen itself does not burn, but it dictates how fast and how violently everything else burns. Under these conditions, the very metal of the turbine blades wants to spontaneously combust. The friction of the spinning machinery alone is enough to turn the inside of the engine into a molten crater. Simultaneously, the second preburner generates a methane-rich gas to spin the fuel turbine. These two searing high-pressure gases are then smashed together inside the main combustion chamber at pressures exceeding 300 bar over 300 times the atmospheric pressure at sea level. The engine is a perfectly balanced, closed-loop ecosystem of fire, operating on the absolute bleeding edge of metallurgical failure, and the super heavy booster does not use one of these engines. It uses 33, when 33 full-flow staged combustion engines ignite simultaneously. The raw energy released defies terrestrial comparison. The acoustic shock wave alone carries so much concussive force that if it is not heavily suppressed by a deluge of water on the launch pad, the sound waves will bounce off the concrete and literally tear the stainless steel rocket apart from the bottom up. It is a controlled cataclysm, generating over 16 million pounds of thrust, physically shoving the massive steel tower into the sky. Yet, for all this apocalyptic power, for all the metallurgical miracles of the Raptor engines and the stainless steel hull, Starship remains handcuffed by the exact same physical laws that govern the SLS. Tsiolkovsky's ghost still haunts the steel corridors. The sheer mass of the vehicle, combined with the immense fuel required to lift it, dictates a cruel mathematical reality. When a Starship reaches low Earth orbit, having exhausted thousands of tons of super-chilled methane and oxygen, it is essentially empty. It has just enough propellant left to orient itself and execute a fiery plunge back through the atmosphere to land on Earth. If the Starship in low Earth orbit wished to ignite its engines and set a course for Mars, it couldn't. It wouldn't even have the delta-V required to break out of Earth's gravity well, let alone carry the 100 tons of cargo, the life support systems, the food, and the heavy radiation shielding required to keep humans alive across the void. The heavy reusable steel hull that protects it during re-entry is a dead weight in orbit. The rocket equation demands a sacrifice, and Starship refuses to shed its stages. To bypass this absolute physical barrier, to cheat the natural logarithm of the mass ratio without throwing the ship away, the engineers have wagered the entire future of the architecture on a single, terrifyingly complex maneuver. A maneuver that fundamentally alters the nature of spaceflight, yet introduces a logistical nightmare of such unprecedented scale that it threatens to collapse the entire Mars endeavor before it even begins. They must refuel the ship in the darkness of orbit. It sounds deceptive in its simplicity. We refuel fighter jets in midair. Why not spacecraft in orbit? But the vacuum of space is not the sky. In the frictionless, microgravity environment of low Earth orbit, thermodynamics and fluid mechanics morph into something alien and hostile. When you shut down the engines, the artificial gravity of acceleration disappears. Inside the cavernous steel tanks of the Starship, the remaining cryogenic methane and oxygen no longer pool neatly at the bottom near the plumbing. They become floating, chaotic blobs of freezing liquid adhering to the walls, drifting aimlessly through the vast interior. If you attempt to open a valve to transfer these liquids to another ship, you cannot guarantee that you are pumping liquid at all. You are just as likely to pump the pressurized ullage gas, completely destroying the delicate pressure equilibrium of the tanks. Worse still, the sun in orbit is an unblinking, unshielded eye. The side of the stainless steel ship facing the sun absorbs massive amounts of solar radiation, heating up dramatically, while the side facing the dark void of space plunges to temperatures approaching absolute zero. This immense thermal gradient causes the delicate cryogenic liquids inside to boil off, converting back into gas. Every hour spent coasting in orbit, the lifeblood of the ship is slowly, inexorably vanishing into vapor. To refuel a Starship for Mars, a second ship, a massive tanker filled to the brim with explosive cryogenics, must launch, chase the target ship down at Mach 23, dock with millimeter precision in the pitch blackness of Earth's shadow, and somehow force thousands of tons of freezing, boiling liquids from one tank to another without the entire system freezing shut, overpressurizing, or detonating. But one tanker is not enough. The mathematics of the rocket equation are unforgiving. To fully fill the tanks of a single, Mars-bound Starship waiting in orbit, it requires between 8 and 16 dedicated tanker flights. This is the brutal, unyielding arithmetic of the orbital refueling architecture. To push a single, fully burdened Starship out of Earth's gravitational well and cast it toward the red planet, you must first orchestrate a logistical pipeline of such staggering complexity that it defies the entire history of aerospace operations. You cannot simply launch a rocket, declare victory, and go home. You must treat the most complex, violent machine ever engineered by human hands as if it were a commercial cargo plane, turning it around and firing it back into the void again and again and again within a matter of days. Consider the mechanical reality of this launch cadence. When the Super Heavy booster returns to the launch site, it is not a pristine vehicle. It has just endured the concussive trauma of 33 Raptor engines detonating simultaneously, followed by the aerodynamic violence of falling backward through the atmosphere at supersonic speeds. Its stainless steel skin has been subjected to immense thermal expansion and contraction. Its intricate network of propellant lines, valves, and turbopumps has been bathed in cryogenic freezing cold and then scorched by the searing heat of re-entry. To launch this machine 15 times in a single month to fuel one waiting Starship requires a ground infrastructure that borders on science fiction. The launch pad itself becomes the ultimate bottleneck. You must inspect miles of welds, verify the integrity of thousands of heat shield tiles, pump millions of pounds of violently reactive liquid oxygen and liquid methane into the tanks, and ignite the tower all over again before the orbital window closes. If a single valve sticks, if a sensor throws a false positive, if a localized weather cell moves over the launch site bringing high winds or lightning, the entire chain halts. And while the launch pad sits idle, the clock in orbit is relentlessly ticking. The target ship, holding whatever cryogenic fuel has already been delivered, is trapped in the unforgiving glare of the sun. The thermodynamics of low Earth orbit are a nightmare of extremes. Every 90 minutes, the spacecraft crosses from the searing, unfiltered radiation of orbital daytime, where temperatures can spike to 120 degrees Celsius, into the absolute, freezing darkness of Earth's shadow, plunging to minus 150 degrees. This violent thermal cycling acts as a relentless pump, transferring heat through the stainless steel hull and into the super-chilled propellants inside. The liquid methane and liquid oxygen begin to boil. They convert back into gas, expanding rapidly and raising the internal pressure of the tanks to critical levels. To prevent the ship from bursting like a fragmented bomb, it must constantly vent this precious gas out into the vacuum. This is the boil-off paradox. It is a thermodynamic hourglass bleeding your delta V into the void. If your launch cadence on the ground falters, the ship in orbit will eventually vent propellant faster than your tankers can deliver it. You will find yourself trapped in a Sisyphean nightmare, burning millions of dollars in launch costs just to replace the fuel that boiled away while you were waiting for the weather to clear. But even if you can master the cadence, even if the launch pad operates with the cold, flawless precision of a metronome, you still have to execute the physical transfer of the fluids. Catching a target in orbit is an exercise in counterintuitive physics. If you are trailing a spacecraft in the same orbit and you fire your engines to accelerate toward it, your added kinetic energy causes your orbit to widen and rise, moving you into a higher, slower path. You will actually fall further behind. To catch the ship ahead of you, you must decelerate, dropping into a lower, faster orbit to undercut your target, before violently firing your engines again at the precise mathematical second to match velocities and rise back up to meet it. This orbital ballet happens at 28,000 kilometers per hour in total silence over the dark oceans of Earth. Once the two massive steel leviathans make physical contact, docking nose to nose or belly to belly in the blackness, the true engineering terror begins. You cannot simply open a valve and turn on a pump. In the frictionless microgravity environment of space, liquids do not behave like liquids. Without the invisible hand of gravity to pull the propellants to the bottom of the tanks, the cryogenic oxygen and methane become floating, chaotic blobs of freezing fluid, drifting aimlessly through the cavernous interior, clinging to the walls through surface tension, and trapping massive pockets of pressurized gas within them. If you attempt to run a mechanical pump in this environment, it will suck in a mixture of liquid and gas. The pump will cavitate. The rapidly spinning metal impellers will bite into empty voids of gas, overspin, and then violently smash into the dense liquid, generating immense shock waves that can shatter the turbine blades and instantly destroy the spacecraft. To move the fluid, you must rely on a maneuver known as an ullage burn. While the two ships are locked together, moving at Mach 23, they must fire small thrusters to create a microscopic, sustained forward acceleration. This tiny, continuous thrust creates a localized, artificial gravity field. It forces the chaotic blobs of floating cryogenic liquid to slowly settle against the aft bulkheads of the tanks, covering the intake valves. Only then, while still firing the thrusters to maintain this fragile artificial gravity, can the valves open and the pressure differential force the super-chilled liquids from the tanker into the target ship. Imagine the thermodynamic shock of this process. You are taking thousands of gallons of fluid, sitting at nearly absolute zero, and forcing it through cold steel pipes that have been baking in the orbital sun. The moment the liquid touches the relatively warm metal of the transfer lines, it instantly flashes into vapor, expanding hundreds of times in volume. creating a localized pressure spike known as a water hammer. This invisible kinetic shockwave travels back through the plumbing at the speed of sound, carrying enough brute force to blow the valves right out of their housings. The transfer must be managed with microscopic precision, chilling the lines down slowly, balancing the pressure between the two ships as they fly locked together in the dark. A single failure in this sequence, a single stuck valve or loss of ullage thrust, could result in the catastrophic rupture of both vehicles, instantly turning thousands of tons of propellant into an expanding cloud of orbital shrapnel. This is the barrier of the reusable architecture. It requires humanity to transform deep space from a realm of bespoke, isolated exploration into a bustling, industrialized shipping lane. It demands a flawless orchestration of orbital mechanics, thermodynamic management, and mass manufacturing that leaves absolutely zero margin for error. Faced with this impossibly fragile logistical chain, the legacy aerospace establishment points back to the Space Launch System and the disposable architecture as the only sane, reliable path forward. Why risk the entire mission on the unproven, dangerous choreography of orbital refueling? Why not just build a rocket big enough to throw the payload directly toward Mars, as we did during the Apollo era? But the disposable architecture harbors its own fatal, mathematical disease. It is a disease not of orbital mechanics, but of time, capital, and industrial physics. To bypass the need for orbital refueling, the traditional approach dictates that you must assemble the Mars mission piece by piece, using super heavy lift rockets. You need a transit habitat for the crew to live in during the 9-month journey. You need a massive propulsion stage to execute the transmortion injection burn. You need a dedicated descent module to survive the terrifying plunge into the Martian atmosphere, and an ascent module to blast the crew back off the surface. Because of the tyrannical mass ratio of the Tsiolkovsky equation, the SLS cannot lift all of these components at once. It must launch them individually into a high lunar orbit, assembling a sprawling, modular spacecraft over a period of years, waiting for the perfect planetary alignment to finally depart. The barrier here is the sheer, agonizing pace of manufacturing. The core stage of the SLS is a bespoke, artisan machine. It is not mass-produced in a factory. It is practically handcrafted. The massive aluminum-lithium propellant tanks are joined using a complex technique called friction stir welding, where a spinning metal pin heats and physically smears the molecular structure of the metal panels together. It is a slow, painstaking process. Every inch of the weld must be subjected to microscopic X-ray inspection, because the slightest imperfection, avoid the size of a grain of sand, will cause the entire rocket to unzip like a tin can under the colossal aerodynamic pressures of launch. The RS-25 engines at the base of the rocket are the crown jewels of American aerospace, salvaged from the retired space shuttle fleet and upgraded at immense cost. Because the rocket is designed to be thrown away every single time an SLS launches, 4 of these irreplaceable, multi-million-dollar thermodynamic masterpieces are intentionally dropped into the ocean and destroyed forever. The supply chain required to forge new engines, to cast the intricate turbopump housings, to machine the regenerative cooling channels, is so specialized and so slow that the industry can barely produce enough hardware to support one launch every 12 to 18 months. And the cost of this artisanal approach is apocalyptic. A single launch of the Space Launch System consumes roughly $4 billion. To assemble the necessary tonnage for a crewed Mars mission using the SLS architecture would require a half-dozen launches. It would consume tens of billions of dollars before the crew even leaves the Earth-Moon system. This is a financial gravity well that no government on Earth can sustain. Tsiolkovsky's equation dictates that the rocket must be enormous. The economics dictate that throwing an enormous rocket away is financial suicide. But the true danger of the disposable, slow assembly architecture is the silent killer of deep space, time. If you are forced to launch the pieces of your Mars vehicle over a span of 5 or 6 years, those components are sitting in the irradiated, hostile vacuum of space, waiting. The universe does not wait passively. The delicate optical sensors used for navigation are slowly sandblasted to opacity by micrometeorites. The extreme thermal cycling degrades the structural seals and hardens the synthetic lubricants in the docking mechanisms. The constant bombardment of galactic cosmic rays slowly flips the microscopic bits in the solid-state memory of the avionics computers, corrupting the code that will eventually be required to land the crew on another planet. By the time the final component is launched and the crew finally arrives to assemble the ship, the hardware that was launched first is already obsolete, degraded, and creeping toward catastrophic failure. You are racing against the decay of your own machinery before the mission has even begun. This is the ultimate paradox of our expansion into the cosmos. The universe has trapped us in a binary choice between two impossible realities. If we choose the radical path of full reusability, we must master an unprecedented, terrifying choreography of mass launch cadence and cryogenic orbital refueling. We must treat highly explosive, super-chilled propellants in microgravity as if they were water flowing from a tap, relying on a logistical chain so fragile that a single thunderstorm in Texas could cause a cascading failure of the entire Mars window. We must bet the lives of the crew on the assumption that we can routinely perform a ballet of orbital docking and fluid transfer that has never been successfully demonstrated at this scale. If we choose the conservative path of disposable brute force engineering, we surrender to the slow, agonizing death of capital and time. We accept a launch cadence so sluggish that the hardware decays in the vacuum before it can be used. We accept an economic model that treats miraculous engineering as disposable trash, guaranteeing that our presence in deep space will remain a rare, fleeting stunt rather than a permanent colonization. And looming over this agonizing engineering paralysis is the ultimate, immovable deadline. Mars does not care about our budgets, our welding techniques, or our boil-off rates. The planets are massive, in different clockwork gears, grinding through the dark. Every 26 months, the synodic window opens. For a few brief weeks, the geometry of the solar system aligns, and the delta V required to cross the abyss drops to a barely manageable level. If you miss this window, the planets drift out of phase, and the required energy to make the crossing spikes to an impossible magnitude. You are stranded on Earth for another 2 years. Both architectures are barreling toward this terrifying celestial bottleneck. Starship must prove it can rapidly refuel before the window closes, racing against the thermodynamics of boiling methane. SLS must prove it can build and assemble its multi-billion-dollar puzzle pieces before the window closes, racing against the decay of its own isolated hardware. The barrier is no longer just the gravity of Earth. The barrier is the realization that our current understanding of physics, our mastery of materials, and our economic models are fundamentally incompatible with the reality of the solar system. We are trying to cross an ocean using two different types of sinking ships, fully aware that the water is rushing in, but unable to agree on which leaks to plug first. As we push the limits of these machines, as the metal groans under the pressure of 300 atmospheres and the engines scream against the chains of Tsiolkovsky's mathematics, a much darker, unspoken truth is beginning to emerge from the data. The unspoken truth emerging from the telemetry, the budget reports, and the agonizing failures on the test stands is that we are fundamentally misinterpreting the nature of the cosmos. We view the vast distances between planets as empty space, a passive void simply waiting to be crossed, like an ocean before the age of sail. But the mathematics of the ideal rocket equation and the brutal realities of thermodynamics tell a radically different story. Space is not passive, it is an active, fiercely enforced quarantine zone. When astrophysicists and cosmologists look at the fundamental constants of our universe, the strength of gravity, the speed of light, the energy density of chemical bonds, they often speak of the anthropic principle, the comforting idea that the universe is perfectly tuned for life to exist. But if you look at those exact same constants from the perspective of an aerospace engineer, they do not look like a cradle. They look like the walls of a maximum security prison. Consider the cruel equilibrium of our physical reality. If Earth were just 50% more massive, the increased gravity would require a delta V so immense that chemical rockets would be mathematically incapable of achieving orbit. We would be permanently, physically trapped, regardless of our technological advancement. Conversely, if the energy density of liquid oxygen and methane were just slightly higher, spaceflight would be a trivial, everyday occurrence. Instead, we exist in a razor-thin, agonizing margin. We are just light enough to leave, and just heavy enough that leaving requires nearly every ounce of our planetary resources and industrial capacity. The universe has given us exactly enough rope to hang ourselves in the attempt. This is the hidden consequence of the battle between the Starship architecture and the space launch system. We are not merely trying to solve an engineering bottleneck, we are attempting to violate a physical quarantine that has kept the cosmos dark and silent since the Big Bang. For decades, scientists have wrestled with the Fermi paradox, the terrifying contradiction between the high mathematical probability of extraterrestrial intelligence and the absolute lack of empirical evidence for it. We have scanned the heavens for radio signals, for the dimming of stars behind Dyson spheres, for the infrared exhaust plumes of interstellar engines, and we have found nothing but a deafening, dead silence. We have hypothesized about the great filter, a theoretical barrier that wipes out civilizations before they can expand across the stars. We have imagined this filter as a sudden, dramatic apocalypse, global nuclear annihilation, rogue artificial intelligence, or runaway ecological collapse. But as we stare at the frozen, complex plumbing of a Raptor engine, or the violently discarded wreckage of an SLS core stage sinking to the bottom of the ocean, a much colder, less glamorous reality comes into focus. The Great Filter is not a singular, dramatic event. It is the rocket equation. It is the sheer, suffocating, thermodynamic cost of moving biological mass out of a gravity well. Across the billions of galaxies in the observable universe, there may be countless intelligent species looking up at their own alien moons, building their own towering monuments of steel and fire, only to run into the exact same mathematical wall. They realize that to establish a permanent presence beyond their atmosphere, they must bankrupt their planetary economy, orchestrate impossible logistical chains, and fight the relentless, grinding decay of entropy. And so, they simply stop. They turn their gaze inward, they build virtual realities, or they slowly fade into extinction on the rock where they were born, quietly ground to dust by the gears of time. The silence of the universe is not the absence of life. It is the sound of millions of species surrendering to the unyielding laws of physics. And if we refuse to surrender, if we somehow force our way through this filter using brute force or radical reusability, the consequences for humanity are far darker than our optimistic science fiction suggests. The aerospace industry treats the human payload as just another variable in the mass ratio, a static allocation of kilograms on a spreadsheet. But biology is not cargo. It is a terrifying, parasitic liability. We are complex bags of salt water, fragile proteins, and microscopic electrical impulses optimized over millions of years to exist in a highly specific, nurturing planetary oasis. To keep a human alive in the deep void, a spacecraft cannot merely be a vehicle. It must be an active, synthetic emulation of Earth. Every single breath a crew takes requires heavy chemical scrubbers to remove toxic carbon dioxide. Every drop of water must be endlessly recycled from sweat and urine through massive energy-dense filtration systems. Our bodies, deprived of the constant, invisible stress of Earth's gravity, begin to immediately dismantle themselves. The skeletal system, sensing it no longer needs to support weight, begins to reabsorb bone density, leaching calcium into the bloodstream and forming agonizing kidney stones. The heart, no longer forced to pump blood uphill against gravity, physically shrinks and weakens. The optic nerve swells in microgravity, flattening the back of the eyeball and permanently degrading vision. We are a species that literally dissolves when removed from our planetary context. If we succeed in placing this fragile biological machinery on the surface of Mars, we are not expanding humanity, we are severing it. The romanticized vision of a multiplanetary species assumes a unified human empire, trading goods, culture, and ideas across the void. But the physical reality of the solar system prohibits this. The transit time between Earth and Mars is not measured in days or weeks. It is a grueling, 9-month voyage through a radioactive wasteland. This is not a commute, it is a permanent exile. The communication delay of up to 44 minutes guarantees that no organic conversation, no rapid debate, no real-time human connection can ever occur between the two planets. But the true severance will not be cultural or political. It will be biological. The gravity on Mars is only 38% that of Earth. There is no breathable atmosphere, no magnetosphere to shield against the relentless, invisible bombardment of galactic cosmic rays. The first humans who managed to survive the logistical nightmare of the journey and the terror of the descent will be forced to live out their lives deep underground, entombed in shielded habitats, relying on the flawless operation of mechanical life support systems for every single second of their existence. If they reproduce, the consequences will be irreversible. A child born in the 1/3 gravity of Mars will develop a radically different skeletal and muscular structure. Their cardiovascular system will be optimized for a world where walking requires vastly less effort. If that Martian-born human ever attempted to return to Earth, the crushing gravity of our home planet would feel like a relentless centrifuge. Their bones would shatter under their own weight. Their heart would fail to pump blood to their brain. They would be physically marooned. Within a few short generations, the harsh, unforgiving environment of Mars combined with the absolute genetic isolation enforced by the vast distances of space, will trigger an evolutionary divergence. The background radiation will subtly mutate their DNA. The low gravity will stretch their limbs and thin their frames. The total reliance on artificial, enclosed ecosystems will fundamentally alter their microbiomes and immune systems. We are not building a colony. We are building a speciation engine. The battle between Starship and the space launch system is, therefore, the catalyst for the end of Homo sapiens as a singular, unified entity. If these machines succeed, if they finally crack the mathematical prison of the mass ratio and establish a permanent, logistical bridge across the dark, the creatures that eventually look back at Earth through their telescopes will not be human. They will be an alien species of our own making, forged in the freezing, irradiated crucible of a dead world. And this forces us to confront an even more terrifying philosophical abyss. Why are we doing this? When we strip away the noble rhetoric of exploration and the innate human desire for discovery, the push to conquer Mars is driven by a deep, existential dread. It is a quiet, collective acknowledgement that Earth is a single point of failure. We look at the geological record and see the violent scars of asteroid impacts, the global ash layers of supervolcanoes, the silent, frozen epochs of deep ice ages. We know, with absolute mathematical certainty, that eventually our planet will become uninhabitable, whether by our own hands, through ecological collapse or nuclear fire, or by the slow, inevitable expansion of our dying sun. The biosphere will eventually boil away into the vacuum. Mars represents the ultimate life insurance policy for consciousness, but it is a policy that requires us to sacrifice our very identity to collect the payout. The architecture of our survival demands that we systematically transform ourselves into machines. We are already seeing the precursors to this transition on the launch pads today. The sheer, overwhelming complexity of an orbital refueling maneuver, the microscopic precision required to land a 100-ton steel cylinder on a floating oceanic platform, the thermodynamic balancing act of a full-flow staged combustion engine. These are systems that have long surpassed the limits of human reaction time. They are governed entirely by autonomous algorithms, executing thousands of calculations per millisecond, reacting to pressure spikes and thermal anomalies far faster than a human brain could even register the sensory data. The rockets are already thinking for themselves. The biological crew strapped into the payload fairing is merely the most inefficient, fragile, and demanding component of the entire system. In the cold, unyielding calculus of the void, consciousness is a massive logistical liability. It requires constant atmospheric pressure, specific temperature ranges, psychological stability, and a massive footprint of consumable resources. A machine requires only a solar panel and a heat sink. As we push further into the deep, the biological constraints of our bodies will become increasingly intolerable. The future of deep space exploration may not belong to the fragile descendants of Earth, struggling to maintain their sanity in subterranean Martian caves. It may belong entirely to the descendants of the machines we are building right now. Artificial intelligence, housed in hardened silicon and radiation-resistant stainless steel, requires no cryogenic life support, suffers no catastrophic bone loss in zero gravity, and is completely immune to the genetic shredding of cosmic radiation. The grand, multi-billion-dollar battle between NASA's disposable legacy and SpaceX's reusable ambition might not be the dawn of a new human age. It might simply be the biological scaffolding required to birth our synthetic successors. We are burning through the last easily accessible fossil fuels of our planet, exhausting the chemical energy reserves accumulated over hundreds of millions of years just to construct the very mechanisms that will ultimately render us obsolete. We are acting as the biological bootloader for a mechanical civilization that will eventually inherit the silence of the stars. The closer we examine the data, the more the illusion of our cosmic destiny begins to shatter. The numbers are totally indifferent to our ambition. The void is aggressively, actively hostile to our biology, and the machines we have built to conquer the dark are quietly demonstrating that they are vastly superior suited for it than we will ever be. We are pouring our wealth, our intellect, and our fragile lives into a mathematical paradox, fully aware that the only way to survive the journey is to stop being, to look upon the cosmos and believe it is a frontier waiting to be conquered, is the ultimate manifestation of biological arrogance. We stand at the bottom of our atmospheric ocean, looking through the atmospheric distortion, and project our terrestrial concepts of destiny onto a scattering of ancient, uncaring photons. We imagine the stars as a theater constructed for our eventual arrival, but the universe does not know we are here. It is a blind, grinding mechanism of thermodynamics and gravity, completely indifferent to the millions of joules of chemical energy we violently detonate in our desperate attempts to claw our way off this rock. Mars is not waiting for us. It is not a sanctuary. It is a sterilized, irradiated corpse of a planet, spinning silently in the dark as it has done for billions of years before the first hominid stood upright, and as it will continue to do long after the last human consciousness flickers out. When the first heavy boots finally press into that rust-colored dust, the cosmos will not pause to acknowledge the achievement. The natural logarithm of the mass ratio will not suddenly soften. The radiation will not yield. The margins of survival will remain exactly as razor-thin, exactly as merciless as they were the moment the launch pad clamps released. The battle between the disposable monuments of our past and the reusable silos of our future is, ultimately, a symptom of a species terrified of its own expiration date. We are building these leviathans of fire and steel because the alternative is absolute psychological collapse. To accept that we are merely a temporary, localized chemical anomaly, forever confined to a single, decaying sphere of rock, is a truth too heavy for the human mind to bear. And yet, in our desperate attempt to outrun the death of our star, we are actively engineering the death of our own humanity. The bridge we are forcing across the void is not designed for the flesh and blood that exists today. It is a filter that will meticulously strip away our biology, leaving only the cold, synthetic architecture of the machines we built to carry us. We are translating ourselves into data, into telemetry, into algorithms that can survive the absolute zero of the shadows and the ionizing glare of the unshielded sun. Someday, the final chemical rocket will launch. The final transfer window will close. The vast, expanding silence of deep space will swallow the fading echoes of our mechanical ambition. What remains on the shores of other worlds will not be human, but a monument to a species that refused to die quietly. There will be no grand revelation in the dark. There will only be the indifferent mathematics of celestial mechanics, the slow decay of abandoned steel, and the chilling, undeniable reality that we have exiled ourselves into an abyss that was never meant to hold us. The stars will continue to burn out. The galaxies will continue to accelerate apart. and the void will remain exactly as it has always been, endless, perfect, and absolutely cold.